Welcome to Quantum, a channel dedicated to theoretical physics, with all its rigorous mathematical underpinnings and profound philosophical implications.
Today's lecture is organized as follows. 1. Summary, from phase spaces to symplectic manifolds. A review of how classical phase spaces naturally lead to the structure of symplectic manifolds. 2. From symplectic manifolds to Hilbert spaces. We will discuss the quantum conditions, present an example through the quantization of the cotangent bundle T star Q, introduce group-theoretic quantization, and explain the role of maximally commuting observables and polarizations. 3. Prequantization, geometric quantization 1, covering the Prequantum Assignment and the construction of the Prequantum Assignment. Summary, from phase spaces to symplectic manifolds. In classical mechanics, we distinguish between two key types of spaces, the configuration space and the phase space. The configuration space, denoted by capital Q, is the space of possible positions of a system. Each point in Q corresponds to a unique configuration described by generalized coordinates Q superscript I. By contrast, the phase space contains more information. It captures not only the positions but also the momenta associated with motion. Thus, the phase space describes the full dynamical state of the system at any instant. Mathematically, the phase space is realized as the cotangent bundle of the configuration space, denoted by capital T star Q. Let us understand this construction more carefully. At each point Q in the configuration space Q, there is an associated cotangent space, consisting of linear functionals on the tangent space. This cotangent space is denoted by capital T star subscript QQ. The cotangent bundle is simply the collection of all these cotangent spaces, gathered smoothly over the entire configuration space. Thus, the phase space T star Q combines positions and momenta in a natural geometric framework. In local coordinates, we describe a point in phase space by the values of the position coordinates Q superscript I and their conjugate momenta P subscript I. The momenta are called fiber coordinates. They measure how functions on Q change in various directions. Now, phase space is not just a manifold, it carries additional structure. It is equipped with a canonical symplectic form denoted by the Greek letter omega. This symplectic form arises naturally from a simpler object, the canonical one form, often called the Liouville one form, denoted by the Greek letter theta. The Liouville one form encodes the pairing between positions and momenta. Taking the exterior derivative of theta gives the symplectic form omega. Locally, the symplectic form measures infinitesimal areas in phase space. Globally, its top power measures the total symplectic volume. The symplectic form omega has three fundamental properties. First, it is closed, meaning that the exterior derivative of omega denoted d omega is 0. Second, it is exact in cotangent bundles, meaning omega globally arises as the exterior derivative of theta. Third, it is non-degenerate, meaning that the associated matrix is invertible and defines a valid structure. In other words, the determinant of omega is non-zero. Moreover, because of non-degeneracy, phase space must have an even number of dimensions. An extraordinary result of symplectic geometry is Darboux theorem. It states that all symplectic manifolds are locally equivalent. No matter how complicated their global structure may be, locally the symplectic form omega can always be written in the standard flat form. Explicitly, in local coordinates, omega equals the sum over I from 1 to n of dp subscript I wedge dq superscript I. Thus, symplectic geometry has no local curvature invariance. Only the global properties distinguish different symplectic manifolds. To summarize, a symplectic manifold is a smooth manifold equipped with a closed, non-degenerate two-form omega. The closedness condition means that d omega equals 0. The non-degeneracy condition means that at each point, if omega evaluates to 0 when paired with every vector, then the original vector must itself be 0. This ensures that phase space has a well-behaved invertible structure. It also implies that the dimension of the manifold must be even. The symplectic form omega allows us to bridge geometry and dynamics. It establishes a natural isomorphism between tangent and cotangent spaces. Given a function f called an observable, we associate a vector field x subscript f called its Hamiltonian vector field by requiring that the contraction of x subscript f with omega equals minus the differential of f. This relation determines x subscript f uniquely. In particular, a distinguished function, the Hamiltonian, governs the evolution of the system. Its associated vector field, x subscript h, dictates the time evolution according to Hamilton's equations. In local coordinates, Hamilton's equations take the familiar form. The time derivative of q superscript I equals the partial derivative of h with respect to p subscript I, and the time derivative of p subscript I equals minus the partial derivative of h with respect to q superscript I. Thus, the symplectic structure encapsulates the entire dynamics of the system. The flow generated by a Hamiltonian vector field preserves the symplectic form omega. This invariance defines symplectomorphisms, transformations that leave omega unchanged. They generalize the idea of canonical transformations in classical mechanics. Thus, the evolution of a system remains within the realm of symplectic geometry, preserving its fundamental structure. The antisymmetry of omega naturally leads to the definition of the Poisson bracket. Given two functions f and g, their Poisson bracket, denoted by curly braces, is defined by evaluating omega on their Hamiltonian vector fields. The Poisson bracket satisfies antisymmetry, linearity, the Leibniz rule, and the Jacobi identity. Together, these properties make the space of observables into an infinite-dimensional Lie algebra. In particular, by using the Jacobi identity, we find that the commutator of the Hamiltonian vector fields, x sub f and x sub g, equals the Hamiltonian vector field of the Poisson bracket of f and g. This shows that Hamiltonian vector fields form a Lie algebra, where the bracket operation reflects the associative structure encoded by the Jacobi identity. Finally, in quantization, we replace the Poisson bracket with the commutator of quantum operators. Specifically, the commutator of the quantized operators f hat and g hat is proportional to minus I h bar times the quantization of the Poisson bracket of f and g. Here, I is the imaginary unit, and h bar is Planck's constant divided by 2 pi. Thus, symplectic geometry provides the foundational structure that seamlessly transitions from classical dynamics to quantum theory. From symplectic manifolds to Hilbert spaces. Quantum conditions. In classical mechanics, the space of observables carries two algebraic structures. First, it behaves like a commutative algebra under pointwise multiplication. Multiplying two functions at each point simply gives a new function at that point. Second, it carries a Lie algebra structure through the Poisson bracket, making it what mathematicians call a Poisson algebra. However, when we move to quantum mechanics, this neat structure breaks. The multiplication of observables becomes non-commutative. In general, the product of two quantum operators does not depend simply on their values at a point, but rather on the order in which the operators are applied. Quantization, therefore, is the process of assigning to each classical observable an operator on a Hilbert space. This assignment must satisfy several important conditions. First, linearity. The quantization map should respect linear combinations. Second, identity preservation. The classical constant function, the function always equal to 1, must correspond to the identity operator. Third, the reality condition. Real-valued classical observables should become self-adjoint operators in quantum theory. Fourth, Dirac's quantum condition. The Poisson bracket of classical observables should correspond up to factors of Planck's constant to the commutator of their quantum counterparts. Finally, a fifth condition, called the irreducibility condition. The quantum operators corresponding to a complete set of classical observables should generate an irreducible set of operators on the Hilbert space. Altogether, these conditions express the central idea that while we lose the classical commutativity, we retain the deep structure encoded by the Poisson bracket. However, it is important to recognize a limitation. In general, it is impossible to satisfy all these conditions simultaneously for all observables. Thus, in practice, we settle for an optimal compromise. We may impose the Dirac condition only on a complete set of observables and extend it to others as far as possible. But selecting a complete set of observables is itself not canonical. Different choices may lead to different quantum theories with different physical consequences. Because of these challenges, geometric quantization proposes a different path, building quantum theory directly from the geometry and topology of classical phase space. This approach aims to be more intrinsic, less dependent on arbitrary choices. Example: quantization of the cotangent bundle. Let us see these ideas at work through an example. We consider the simplest case, a phase space given by the cotangent bundle of a real vector space. Here, the natural complete set of observables consists of the position coordinates and their conjugate momenta. Classically, these satisfy canonical Poisson brackets. Under quantization, these observables must satisfy the canonical commutation relations, leading to what is called the Heisenberg algebra. According to a celebrated mathematical result, the Stone-von Neumann theorem, all irreducible representations of the Heisenberg algebra are essentially the same. They are all unitarily equivalent to the familiar Schrödinger representation on square integrable functions. Thus, in this simple setting, quantum mechanics takes the familiar form of wave functions on configuration space, where positions act by multiplication and momenta by differentiation. Beyond these linear observables, one can attempt to quantize quadratic functions of position and momentum, such as the classical kinetic energy. However, ordering ambiguities arise when we try to quantize mixed terms involving both position and momentum. To maintain consistency, one adopts a symmetric ordering convention. At the algebraic level, these quadratic observables form the symplectic Lie algebra, reflecting the symplectic symmetries of phase space. Yet when attempting to quantize even more general observables, such as cubic or higher degree polynomials, we encounter a fundamental obstruction. This is the Groenewold-Van Hove no-go theorem. It tells us that no quantization can consistently map all classical observables to quantum operators while preserving the essential structures. Thus, a full quantization of all classical observables is impossible, even in flat space. This is not a tragedy. In practice, we only need to quantize the observables of physical relevance, typically those associated with symmetries or conservation laws. Finally, when phase space is globally non-trivial, such as the cotangent bundle of a circle, additional care is needed. Canonical coordinates may not be globally well-defined, and naive quantization can miss important global effects, like the quantization of angular momentum. Instead, one must work with globally defined observables and replace the canonical commutation relations by relations reflecting the true global geometry of phase space. Group-Theoretic Quantization. Is there a more systematic way to approach quantization when global canonical coordinates are missing? The answer is yes. In flat space, translations act transitively on phase space, and the Poisson algebra of basic observables reflects the symmetries of translations. In more general settings, whenever a Lie group acts transitively and symplectically on phase space, its Poisson algebra of generators provides a natural substitute for canonical observables. This is called the canonical group of the system. Quantization then becomes a problem in representation theory. We seek irreducible representations of the associated Poisson algebra. Thus, the canonical commutation relations of flat space become, in the general case, the commutation relations of a group adapted to the geometry of the phase space. For example, for the cotangent bundle of a circle, the appropriate group is the Euclidean group in 2 dimensions. Each situation demands identifying the right group and understanding how its action organizes the classical and quantum structures. Maximally commuting observables and polarizations. Geometric quantization refines this idea even further. Instead of seeking a complete set of observables as in canonical quantization, we seek a maximally commuting set. These are observables whose Poisson brackets vanish pairwise. Their level sets foliate the phase space into Lagrangian submanifolds, surfaces along which the symplectic form vanishes. Choosing such a set defines a real polarization. The leaves of the foliation are the integral manifolds of the polarization. In the language of wave functions, this choice means that physical wave functions should be constant along the leaves of the foliation. They vary only in directions transverse to the leaves. Thus, the idea of a real polarization is to reduce the degrees of freedom of wave functions, aligning quantum mechanics with the global geometry of phase space. In geometric quantization, the Hilbert space is built from wave functions that are constant along the leaves defined by a polarization. In the absence of global canonical coordinates, This approach provides a flexible and powerful framework for constructing quantum theories from classical phase spaces. Prequantization, geometric quantization 1. In geometric quantization, quantization is not seen as merely assigning operators to functions. Instead, it is approached as a geometric procedure that constructs the quantum theory directly from the symplectic structure of classical phase space. Rather than treating classical and quantum systems as fundamentally separate, geometric quantization seeks to derive the quantum Hilbert space from the underlying geometry of the classical system itself. It represents a radical and elegant shift in perspective, an attempt to geometrize quantization and give it intrinsic conceptual meaning. Prequantum assignment. At the heart of geometric quantization lies a simple but powerful identity. The commutator of Hamiltonian vector fields mirrors the Poisson bracket of classical observables. This observation suggests a natural first attempt at quantization, to associate to each classical observable a first-order differential operator, specifically the Hamiltonian vector field multiplied by -I times Planck's constant. This assignment respects several key properties. First, linearity. The map from functions to operators preserves addition and scalar multiplication. Second, reality. Because Hamiltonian vector fields preserve the symplectic form, they are divergence-free, which ensures that the associated operators are Hermitian. Third, the commutator correspondence. The commutator of two such operators reflects the Poisson bracket of the corresponding functions, up to a factor of Planck's constant. These properties align closely with the essential features we expect from quantum observables. Q3, reality. Let us take a moment to explain the reality condition more carefully. The prequantum operator acts on wave functions in the Hilbert space of square integrable functions over phase space. Because Hamiltonian flows preserve the symplectic volume form, the associated vector fields are divergence-free. This property ensures that the Hamiltonian vector fields are formally anti-Hermitian. Multiplying by -I times Planck's constant, we find that the resulting operator is Hermitian. Thus, the reality condition is satisfied. Q4, commutator correspondence. Next, the commutator of two such operators reflects the structure of classical mechanics. Indeed, the commutator of two Hamiltonian vector fields produces another Hamiltonian vector field corresponding to the Poisson bracket of the original functions. Thus, this assignment captures Dirac's vision. The classical Poisson structure is deformed into the quantum commutator structure. The prequantum assignment. However, this first attempt is incomplete. It fails to satisfy one important requirement, namely, that the constant function 1 should map to the identity operator. Since the Hamiltonian vector field of a constant function vanishes, this assignment would send constants to 0, not to the identity. To correct this, geometric quantization refines the operator assignment. One introduces a symplectic potential, a one form whose exterior derivative gives the symplectic form. By modifying the operator with terms involving this potential and the function itself, one defines the prequantum operator. This refined operator now satisfies all the required properties: linearity, preservation of the identity, reality, and the correct commutator correspondence. In deeper terms, the prequantum operator can be understood geometrically. It arises naturally when we consider not just functions on phase space, but sections of a complex line bundle equipped with a Hermitian connection. The curvature of this connection must match the symplectic form, scaled by Planck's constant. In this framework, the prequantum operator is the covariant derivative along the Hamiltonian vector field, corrected by the value of the classical observable. This geometric reinterpretation endows the quantization process with profound meaning, tying quantum theory to the topology and geometry of classical phase space. Q3, Hermiticity. Now, let us check that the prequantum operator is indeed Hermitian. The vector field part is divergence-free and thus Hermitian. The terms involving multiplication by real functions are manifestly Hermitian as well. Thus, for real classical observables, the full prequantum operator satisfies the reality condition. Q4, Dirac's quantization condition. Finally, we examine the commutator of two prequantum operators. The dominant contributions come from the vector field terms, which, as we have seen, reflect the Poisson bracket structure. Additional terms arising from the symplectic potential and the functions themselves carefully cancel out, preserving the desired correspondence. Thus, the prequantum operators satisfy Dirac's quantization condition. The commutator of two quantum operators corresponds precisely to -I times Planck's constant times the quantization of the classical Poisson bracket. In summary, the prequantum assignment corrects and refines the naive operator assignment, embedding it naturally into the geometric fabric of phase space. It prepares the ground for the next major step, constructing a true quantum Hilbert space by choosing a polarization, thereby reducing the redundant degrees of freedom and arriving at a fully physical quantum theory. This concludes today's lecture. We explored how classical phase spaces lead to symplectic manifolds, how symplectic geometry provides the structure for quantum Hilbert spaces, and how prequantization begins the geometric formulation of quantum theory. If you found this lecture helpful, please consider subscribing to the channel, leaving a comment, and sharing the video with anyone who might benefit. Your support helps us continue creating content at the intersection of mathematics, physics, and philosophy. Thank you for watching, and see you in the next lecture.